feedback. Questioning is the goal, and it's also the goal to just kind of recognize each other's efforts this far into the semester. Okay, awesome. I'm going to hand it off to Peter.
All right, good morning, everyone. We're going to start us off. I'm going to quickly go through a high-level robot overview. This year, we've decided to set a robot mass of 50 kilograms as the upper limit. Distributed thusly 20 kilograms for drivetrain, 20 kilograms for excavation and deposition, 5 kilograms for P&H, and 5 kilograms for software. This will keep us lightweight while also allowing us enough mass to make mechanically complex and good systems. Overall goals for the 2024-2025 season, we're trying to reduce the mass of our robot, hence the mass limits. We're trying to increase our mining capacity from last year. We're switching to brushless motors due to their increased efficiency and availability. We are increasing dust protection measures. We're improving our resilience against the rocks that can be found in the regolith pits. We're increasing the traction of our drive base, and we're going to be trying to improve the autonomy of our system. All of this will facilitate better performance in the competition and a more robust and reliable robot. Now, with that, I'm going to hand it off to our systems leads to talk about more in-depth robot requirements and system requirements.
All right, so we're starting with systems requirements review, which is sometimes a separate review gate. It's not going to be this year. We do also have a quick little major demographic survey, so if you want to take a couple minutes and fill that out, that would be great. Just scan the QR code up there. I'll give you guys like a minute for that, and if you don't get it done now, it will be also on the slide, so you should be able to find it later. So we're going to start with a quick overview of our engineering life cycle. This graph may look familiar. It has been updated a little bit to account for the fact that we are doing SR combined with SDR this year. Also added some budget reviews on there. But overall, this is the engineering life cycle. So this is where we are in the entire year. We are currently at SDR, so we're in the beginning of the development phase, and we'll move on to fabrication later on, then verification, testing, operations, and disposal. All right, this is the SRR review trackers. So these are what we use to make sure we are prepared for each review gate. If you want to find them, they are under Google Drive in review gates and then in review trackers. So each review gate has their designated review trackers, and this helps us on systems make sure everything is ready for the review gate and what we need to do coming out of it. So for this one, as you can see, everything is good to go. Success criteria, we will go check those off afterwards.
Okay, so next I'm going to discuss the system requirements. We prepared the system requirements this year based on the NASA rulebook, which was released this year, as well as our experience in past years and objectives we had for the robots. There is 4 types of system requirements we have: functional, performance, safety, and implementation. Functional requirements describe what the robot needs to do as it's operating. Performance requirements are characteristics that we want the robot to have. For example, a certain mass limit. Safety are things like how does the robot handle failures, how is it reliable in a variety of different conditions, and implementation are things like what type of materials or mechanisms the robot can and can't use as per the rulebook. So we have the objectives here. Peter already presented on some of those, but some of our technical objectives for this year are minimizing weight, minimizing part count, having fasteners easily accessible, being able to easily remove parts for repair, and incorporating dust-resistant features. The full system requirements list didn't fit on the slide, but you can view it in the drive under the systems folder, and it'll have all the requirements that we've identified for this year. Next, we have technical performance measures. These are related to the mass allocations that Peter presented earlier. So those describe how we want to allocate the different targets that we want the robot to reach in terms of how heavy it is, how much regolith can it move, how quickly can it do a cycle. So they're derived from the system requirements. The sub-team leads create them for their own sub-teams, and they're going to be updated at each review gate as we get new information. So essentially, they're a threshold that components must be within. So here you can see the initial TPMs for the high level of the robot. So as you can see, we have that mass target of 50 kilograms. We also have targets for power, the physical dimensions, storage capacity. These are just our initial ones that we've thought of based on the rules in the rule book and our experience with previous years. But these will be updated from looking at the BOM of the full CAD model, and then later they'll be updated when we have physical parts for the robot. We'll characterize them, and we'll keep updating these to make sure they're within the limits. So this is our schedule, just so you know what's coming in terms of the next reviews. Our next major review is the PDR, the preliminary design review. And then after that, we have a deadline for when you want the design to be done. Then we're going to do the critical design review, and then the test readiness review. And then the next major deliverable after that is the proof of life, which obviously requires us to have the robot completed. So from PDR to CDR, we have about 10 weeks. From CDR to TRR, the test readiness review, we have about 7 weeks. And then from TRR to the proof of life, we have five full weeks, including 2 weeks of testing. So yeah, that's all for systems. Next excavation is going to present.
All right, to start out excavation, I'm going to be discussing some of the things we thought about when we were brainstorming our ideas. So an effective excavation system should be effective at mining. So it should mine quick and have a high volume throughput. It should be easy to manufacture and assemble. It should be reliable, and it should be resilient to stuff like jamming and like breaking, mechanical, or having no mechanical failures. It should also be resilient to dust and gravel. Last year, we had a lot of issues with this, so this is something I'd like to focus on this year. And then also, we want to make it as light as possible because our score this year will be normalized based on weight and time and power consumption. And some system requirements we have is excavation has to fit within the maximum dimensions of the robot. It also has to be fast enough to attempt multiple runs in a time span of 30 minutes. And excavation and deposition combined have to have a mass of under 20 kilos. Based on my approximations of last year, we'll probably sit around 10 to 14 kilos for excavation. This is something we'll have to work with deposition to figure out how we allocate that 20 kilos. And then also we'd like to maximize volume throughput to get the best score in the competition. And then another thing is we have to successfully integrate with the other subsystems in the robot.
Oh, okay. Yep. All right, so this is our first idea for excavation. This is the scup. So how the scup works is it's a continuous rotary mining system, which stores regolith internally inside that big drum. And it has one motor in the middle to rotate the drum and 2 linear actuators to move it up and down. So how it works is it scoops up regolith from the bottom, and as the system completes its rotation, the regolith will just simply fall back into the middle of the system. And if you want to release all the regolith, you spin it the other way, and instead of falling into the system, it'll go back out the way it came and fall back out wherever you want it to. So the pros of this is that it completely integrates excavation and deposition, and it's simple mechanically. And also it saves mass because it's integrating both systems and kind of condenses everything. However, some potential cons are the center of gravity might cause problems because having it completely on one side of the robot means that all of the mass of both excavation and deposition, whatever, even if it is light, is on one side, which means there's nothing on the other side, i.e. deposition, to counter that mass, and that can cause problems. And also, because there's a lot of curves involved in the design of this system, it might be quite hard to manufacture all the sheet metal to get it to curve properly.
All right, so for the bulldozer design, my friend and I were both on the sub team that came up with this design. We really value it because of its simplicity, but we also wanted something efficient. And what can get more efficient and simple than just pushing moon dust around? So we drew a lot of inspiration from the Caterpillar Coal U blade. There are many different designs for bulldozer blades. And when we were looking between the S blade, the U blade, there was an SU blade, there was a wedge blade, we determined that the U blade would be best because this one has a curve to it, which maximizes its capacity for regolith while being able to transport that regolith over longer distances. And effectively, we would be able to go back and forth for multiple runs using the bulldozer here. Then from there, we realized for maneuverability, we can't just tack on this blade to the front of the drivetrain. We need to have a way to lift up the blade, but we also have to keep it within the dimensions of 0.75 meters when it's lowered and the 2.25 meters when it's raised. So when we want to raise it up, there are two methods to doing this. Pictured here, we have the two arms. So we would have four arms that would be linearly actuated. And then our other method would be using a arm that's connected to the far end of the bot that would pivot, and there would be one actuator to pivot that blade around. I'm going to hand that off to my friend Jack now.
As Bree mentioned here, we have two different designs for raising and lowering the blade. The first is a pivot actuator in which the blade is put onto a pivot. One of the main benefits of that is that it has slightly better center of mass because you actually have to weight it in the back of the robot. And then with the other design, which is a 4-bar linkage, you have these 4 bars, as is shown in the diagram above, that will pivot the blade up and down. Main benefit of this is that it keeps the blade in a very rigid position, which is very helpful for when we're moving it around. Moving on from that, we have just for the design as a whole, some of the main benefits is that it's relatively low risk. There's pretty low risk of a mechanical failure. On top of that, it's also very easy to manufacture, similar, and has a lot of the same benefits that SCUP has with simple mechanically and also no deposition, which means that we're just moving the regolith around. That being said, some of the main disadvantages of it is that we are entirely reliant on the traction from drivetrain, which as a result could be problematic if there's not enough traction. Now they have, as was mentioned earlier, redesigned the wheels so they should get more traction, but we won't know that until we've put it into practice. And with that,
Okay, last but not least, we had the bucket elevator. So last year we had a lot of jamming issues with the trencher. Pretty much, we're still a bit unsure about it, but we knew it was caused by the gravel in the pit, which NASA said was supposed to be around 2 centimeters, but it didn't actually end up being that small. So it seems like there's a lot of uncertainty with the size of the gravel in the pit, and the trencher design was not very resilient to it, and we had a lot of issues with jamming and stalling motors and stuff. And so that's why this year we're just going to go back, or we're thinking of going back to the traditional bucket elevator, which is pretty similar to a trencher, except it rotates in the opposite direction and has buckets. As you can see, the arrow rotates up and around the top of the robot. Pretty much the main concern we had with the bucket elevators, we would spew up a lot of dust. So one design improvement we're thinking of this year is adding like a cover to excavation, sort of like what we saw at competition with that could either be like a fabric or or a thin layer of plexiglass to prevent dust from being spewed everywhere and helping guide that dust into the deposition bin. Another improvement I'd like to focus on is improving structural rigidity. Last year we had a little bit of bending in one of our structural plates. I think that was likely caused by placing our structural rods a bit too close together. So we're definitely changing that this year to try and have no bending in our system. Another thing is improving manufacturability. We'll definitely one place we'll improve in this area is by having no scrape plate. That'll definitely make things a bit easier, and as well try and make it a bit more modular. And then hopefully we can improve our bucket designs as well to make them more manufacturable. One thing to note is we'll have new motors this year, so hopefully this will help give us more torque. And hopefully we can mine a bit faster as well.
As for the pros and cons of the system, first off, we have lots of experience developing bucket elevators as well as other similar designs such as the trencher. So we can draw on past successes as well as past missteps to tweak our design to get the best possible bucket elevator as opposed to other designs where we don't have that experience. As well, it's a high total volume throughput as it's a continuous mining type excavator, and as such it will continuously mine, so the volume output would most likely be higher than other designs. Similarly, some cons are it's a bit more complex. There are a lot of moving parts in a bucket elevator, and from our past experience, that can lead to a lot of issues. One such issue is a bucket elevator is more likely to jam. As previously mentioned, gravel being kicked up can get caught in moving parts, and that can prevent it from properly using its motors, and it can get stuck. Also, previously mentioned, another con is bucket manufacturability. As each individual bucket has to be individually manufactured, and for using a lot of buckets, that can be very tedious and difficult to make for our resources that we have.
Okay, last but not least, we have our trade studies. Just take it with a grain of salt. They're not always the most like accurate. It's not the end all be all. This way we make a decision based for a design. So based on the results of our trade study, our bucket elevator placed first, scup placed second, and then bulldozer placed second, and scup placed third. We base this trade study on several criteria such as mining speed, low risk, low mass, more experience, and ease of manufacturability. It seemed like from these results, the bucket elevator seems to be the fastest mining system, which is probably the reason it placed first, and as well, it's probably our lowest risk option since we have a lot of experience with it. In second, we have bulldozer, which is probably the least risky idea in terms of it's very unlikely to fail. So that's what helped boost its score up. And then in third, we have scup, which placed pretty well and did decently in all categories pretty much. Just take these with a grain of salt. This is not like even though we got like a number one, number two, number three, we're considering every single idea equally. So like that concludes excavation. I think, are we gonna open it up to questions? Okay. We think that total volume throughput with the bulldozer, might be a bit lower than a bucket elevator if assuming the bucket elevator works perfectly. This is just based on like anecdotal like proof from competition last year. Top placing teams mostly use continuous mining systems. Yeah, definitely more bulldozing regolith than backing up. We wouldn't actually like pick any regolith up with the bulldozer. We just push it. Yeah, we've thought about that, and it's definitely something we can do. We've also thought about placing the scup in the center of the robot. I've talked a bit with drivetrain a little bit, and they can make it possible. It would just would the only thing is it would definitely limit the size of our scup, which we'll have to do some more looking into to see if that is worth pursuing. Yeah, so we'd probably do two structural plates on the sides of the scup, and then bend sheet metal around in in the pattern of like a circle. It would definitely be pretty difficult. In terms of fasteners, probably rivets. I don't see bolts being. It might be a bit heavy to use a lot of bolts in that way. But that's definitely something we have to look into a bit more. Someone mentioned that it might be good to go and ask people Bechtel about like what their advice is on manufacturing something like this. We're just hoping that we don't hit any rocks or craters. Hopefully our Tommy team can detect those and navigate around it. Yeah, we can move rocks. We'll make our system like structurally rigid enough to be able to deal with any stuff like that. Yeah, we thought about it. It would I would assume it's about the same as its mining speed. Probably a bit faster actually. So I don't think it's that much of a concern. There are things we can change in terms of like the width of like the grooves in the scup that we could alter to make it deposit or mine faster. We were thinking of making scup about have an outer diameter maybe like 10 to 14 inches. This is pretty like preliminary and something we're gonna have to refine more and do more calculations based on like the geometry of scup. It's definitely something that we'll have to consider. And one way we could also improve scup's like volume capabilities just by making it wider. Not necessarily like increasing the diameter, but just increasing the length of the scup itself. Yeah, this is actually like a really big uncertainty we have because based on last year's traction, we probably wouldn't have enough traction to do a bulldozer. Bulldozer is definitely really heavily reliant on drivetrain making effective wheels. So I can't really answer that question at the moment because there's just too much uncertainty about that. Yeah, fortunately this year we happen to have a lot of new members, so I think we do have like the human resources to be able to work on multiple prototypes. So I think we should narrow it down to at least two main ideas. I mean, obviously we know how the bucket elevator works, so we wouldn't make a prototype for that. But something like scup or bulldozer, that's something we could look into. Huh. No, I haven't really thought about that. In terms of rigidity, I just want like good structural rigidity to where like stuff like isn't bending so it doesn't line up properly. Definitely like our upper structural plate last year was bent quite a lot, enough to the point where it was like making it kind of hard to like actually like assemble stuff. So we definitely want to avoid that at least. No, I didn't know that he actually did that, but yeah, I'll definitely reach out to him about it. Okay. We've thought about changing the drums. It's something we want to look into a bit more in terms of total volume throughput of the system. We do have, it seems like we might have access to metal 3D printing again. Not 100% sure, probably gonna have to reach out to see if that's possible. If it is, we'll definitely look into it more. It would definitely make it easier. In terms of weight, I'm not exactly sure if that'd be the best or the lightest option, especially because this year, because weight is more of a consideration, and we only have 20 kilos for excavation and deposition this year. Yeah. Is there any questions like from the live stream? Because I can't see like the. Okay. All right. I guess that wraps up excavation.
So for the deposition, our main goals are to make improvements from last year. So this year's systems has to be much more reliable. It also has to be efficient at berm construction, hold a lot of volume, ideally be light and easy to manufacture. For the system requirements, current dimensions we are aiming for are 20 inches height by 20 inches length by 16 inches width, but those can be expanded if like drivetrain changes the size. We are planning to use 2 or less motors. In some designs, we will not use any motors at all and use linear actuators. Our goal time for the deposition time is under 1 minute. The weight goal is under 10 kilograms. It should not interfere with other systems, and it should be able to complete multiple deposition cycles, especially for like goal of getting autonomous deposition excavation cycles. Is anybody doing conveyor belt? Okay, so for the conveyor belt, the pros of the conveyor belt is consistent and reliable output, and it's relatively low risk if we're doing if we can dust proof it, especially since it cannot get jammed with rocks, and it's basically just more reliable auger. The downsides are it has slow deposition rate. It's pretty difficult to construct, so it's going to be, we don't have experience with that, and it's going to be one of the most complex systems that we are considering. It uses more component, and it might be heavier compared to other options.
The dump truck. So it's probably the most simple design we've had here. It's used in real life, you know, gravel, sand, dirt, and now for us, maybe regolith. So as you see here, Caterpillar dump truck, a little GIF I got for you guys. And with that, I'd like to go on. Oh, yeah, this too. The pros, like I said, it's relatively simple. You can hold a lot of volume inside. And with this combination, it's a relatively low risk system as big rocks, small rocks. There's no real chance of things getting caught or stuck and stuff like that. The cons, however, are the lack in speed. When the actuators are moving, it's going to take time for that bucket to move up, as well as there's going to be center of mass concerns given all of that high volume mass is going to be shifted more and more to the back of the robot. And with that, there's also going to be imprecise deposition compared to like the auger where it could dump in one specific space. This is going to have to dump in a rather larger area. However, there are some ways we can try to mitigate this. It's with like a door at the back, using possibly like magnets to have it close, and when enough weight is on it, shifted when the door is open or the bucket's tilted, then the door will automatically latch open. And other things like that can help reduce like imprecision and even maybe dust concerns.
So next up, we got the trapdoor. This is the simplest design, both easy to manufacture, not a lot of moving parts. It can either be a motor in the bottom left corner here, or a linear actuator at the top in the left picture. It's simple, but there's a couple errors that can happen, like having a large profile. It has to swing around, and it can be very tall. And then it can also limit some other dimensions.
So the auger is last year's design that was used for the 2023-2024 robot. So for the pros, it's relatively mechanically simple system. It was easy to mitigate dust in it. It's not we kind of innovated from last year by designing system to not be to like detect and remove rocks before they get into the auger. It can be made more effective by extending it out so the dust falls down instead of being pushed out. But for the cons, it can be heavy. Rocks can get in between the groups causing jams, which is something that happened last year during the competition. And it's not the fastest system.
So another design idea that we had was a syringe. And basically it's very similar to the dump truck, but we're simply just pushing the regolith out instead of moving the container and emptying it out due to gravity. And there were basically three main methods we could use to actually do this. And one was just using a straight piston to just push it out. And we could have problems with that because it might not be strong enough, or we might need to have space for it. And then we also have another design which uses a piston, but also a like scissor lift. We might want to think of something else. I'm not sure, but that might need more consideration. But the benefit of that is that it is tall, but also not very long. So we might be able to find more space for that design, but it might also be heavier. Another one is the conveyor drive, which is very similar to just a conveyor, except it has a wall to push it along. So that design actually just has like all the benefits and cons as a conveyor, except that it helps push the regolith along. So the pros of the whole thing are really that it's just a simple idea. You're just pushing it out, and it has a large volume because you can make the container as big as you want. The cons of it are that there's a high risk of jam because where the wall actually meets the floor of the container, you could actually get a lot of jamming there unless you have a system like brushes on the bottom or maybe like a really tight fit. It also could be slow because of the linear actuator, and that's something we have taken into consideration. We might want to make a fast system such as the dump truck.
So those are the trade studies for the deposition system. So the number one place is the dump truck, mainly because it's relatively easy to manufacture and it's very reliable. Just because of there's not a lot of things that can fail. The second place is trapdoor, but there's some even though it's on the trade studies is ranked pretty high, it can cause like issues with drivetrain, and the amount of material that we can deposit is going to be limited by the clearance of the robot, so it's not ideal. The third place is auger and conveyor belt. Those are pretty similar in terms of speed, weight, and size. Conveyor belt is more reliable, but harder to manufacture, which is probably going to be the main differences. So, are there any questions? Yeah, so we will either have to have a relatively low dump truck angle, or have some kind of way to move the elevator out, the bucket elevator out of the way, which would be something that we would have to consider. And I would say that's like one of the downsides of the dump truck, is how well it integrates. It might not integrate well with like bucket elevator, or for example, P&H wanted to put their box on top of the deposition, and like if dump truck goes up, it's not really an option. Alex? It's just one of the ideas that we used for the sketch. We would also going to consider the straight, or maybe even tilted towards the back design. It was inspired by the auger from last year, but there's not really a big reason. It's just preliminary sketch. No, it is more harder. It's not much harder. Dump truck is basically just gonna have two linear actuators pushing it up, and like a rigid mechanical, like just rigid like container. I don't know. I think it's just the way that like trade studies, Excel spreadsheet calculated those values. I'm not really sure how to. Yeah, it's on the Google Drive. It should be in the deposition folder. Sophia? Yeah.
Which one do you think would work best with the bucket elevator? I guess, have you guys like talked about what would happen if we were to go with a system that would all excavation?
Like, so for the bucket elevator, I think like the best option would be either conveyor belt or auger, just because it's easier to drop stuff down compared to syringe or dump truck, which might have some kind of issues. And as for combination of the system, personally, I think like it's fine. We can just merge into one big XDEP team and just work on the scab together, or bulldozer together. Peter?
You mentioned on the conveyor belt slide that you thought there would be a somewhat slow excavation system. Can you sort of explain that more? Because I feel like last year's competition, it seems like I was saying that they were actually very fast about this.
I know. I was like, honestly, I think it depends on how we build it. I was kind of I was relatively conservative on that. And also, it would be relatively slow compared to trapdoor, which would be like instant, but it would be like definitely faster than dump truck and auger. Alex? Yeah. I'm glad you asked. We would put some kind of coating that would make it less sticky. I know. As long as it like doesn't stick to the bed of the dump truck, it should like slide down. That's kind of the logic. So potentially we can either use some kind of like non-stick subs cover, maybe like some kind of Teflon or some kind of like material which is designed to be non-sticky, or potentially maybe having some kind of like static charge on the actual like container, which would like repel regolith and make it more slidable. Julian? I don't really have any exact plans yet, but ideally I think like just 3D printing as much possible covers and just hoping it doesn't get in. Potentially maybe exploring some kind of like active dust mitigation, maybe placing some kind of like something that attracts regolith near like some kind of like, I guess, holes that the regolith can get into. Yeah. I feel like potentially the best idea for that would be just tilting it backwards. So even during, and having some kind of maybe door on the back. So in that case, it's going to be somewhat combination of dump truck and conveyor belt. And even if like there's going to be some kind of mechanical issues with conveyor belt, some of the regolith should fall out due to gravity. And it will be easier to start it because it will basically be pushing regolith downside. So there's going to be some gravity assist.
It would be like free hinge, right? That would
Yeah.
open up. So to his point with the weight of regolith, how do you know that that is going to be able to push the door open, and how are you going to like get the magnet to be like specifically strong enough so that it like will open when it's full, but won't open when it's like just driving to where the bird deposit is?
I would assume just like maybe making some kind of experiments and just like just having magnet weak enough so it opens when the dump truck starts tilting, but not enough if there's just a little bit of regolith like falling to the side.
And then another question is with this like the open hinge, if any like how would you dust protect the hinge there? It's just a free hinge, like it's not mechanically powered or anything.
Yeah, I'm not really sure. I haven't thought about that yet. Sophia? Yeah. So that was one of the designs where one of the sides would also move, so it's kind of like opens up like that. Yeah, I would say like as like an actual idea, it's pretty good. It's just like it wouldn't work well with drivetrain, and it's limited by how tall of the berm you can build because of the clearance. Oh, Hans? I would say probably not silage or trapdoor, but I would say mainly conveyor belt, auger, and the dump truck. Peter? Oh.
Or is it like you have the container with regolith and then the back opens up?
Do you want to? Is it fine? Does it work?
Yeah, so for both of these like L-shaped designs, the corner of the L would be where it pivots around, so that entire L would turn. Whether it's a motor that turns it around that pivot or a linear actuator that pushes or pulls the top to turn it around the corner, doesn't really matter. It'll turn the entire thing. and then there's going to be a wall or something else on the other side. When it's upright, no regolith will fall through the crack, or at least a very small amount will. But when it tilts, that gap will open up, more of it will be able to fall out. The only issue again is that it will fall directly under the rover, which could cause problems of how high this has to be from the ground or how separated this has to be from the drivetrain.
Yeah, it's just like one of the iterations. Also, potentially, it might have better weight capacity because if you have a bunch of regolith pushing down, this design would be more or less like less likely to open on itself without when you don't need it to open. Yeah, this would also be one of the ways to do a trapdoor. It will be like closer to like dump trucks. It's gonna be like kind of combination. It's basically gonna be a permanently open dump truck. Yeah.
Having a latch at the bottom, so it would be. I don't know if I can mouse. It would be like in order to have less torque on the motor, which would be back drivable, it would have like a little latch that kept the L at 90 degrees. Peter.
Not yet. I would assume this is something that we maybe should try experimenting just with different, for example, like parchment paper. I would assume it should be relatively good at making a regolith slide. Potentially looking into some kind of like maybe industrially produced like films which are specifically designed to keep material from like sticking. Sophia. I would assume we should definitely experiment with dump truck. And I would assume we are mainly going to focus on dump truck and the conveyor belt because conveyor belt is relatively good for autonomy and just consistency. And for the dump truck is the most mechanically simple and most reliable design that we have so far. Hans? So for like dump truck, I think we should like try to see if like parchment paper actually makes regolith slide. Just maybe going to the pit and seeing what angles we need for it to actually work. Because if it doesn't help that much, we might just abandon it and just go with the conveyor belt. And for conveyor belt, I would say it's mainly CADing and just doing research into how to actually build it. Maybe making some kind of prototypes of different like parts of the conveyor belt, but not like the entire system. Yeah, I would say like mainly like I feel like tilted conveyor belt, which can potentially work as very bad dump truck in case of like mechanical failure. Hans?
Yeah, so thinking about the auger design, obviously, we used it last year to some success. The jamming was a big problem, mostly at the front plate. Was actually the only place that it really experienced. Yeah, most of the primary place we experienced. That could potentially be alleviated by, as Nikolai said, making the auger extend out past the point where there was an under support to which would allow more of the dust to pour out without getting to the back plate. It could also be adjusted by adjusting the geometry of the back plate or some other considerations. I don't know that all of those things would make it all those things would still make it more susceptible to jamming than either a dump truck or a conveyor belt, almost certainly. And neither of those things would do much about the speed, although we do have new motors this year, so we can achieve similar torque to our last system at significantly higher speeds. So potentially it would balance out. Design wise, it would make it more complicated to make that extension. Just because we'd have to, use standoffs or something similar to support the auger, because you need to support the auger on both sides, obviously. So I would say that if we really wanted to, we could make auger work, but I would encourage pursuing the other two designs.
Julian? Something that I kind of thought about is potentially maybe having some kind of sieve between excavation and the deposition, which would like catch like very large pieces of gravel and then kind of like let them slide to the side and off the robot, or potentially just increasing the size of the auger. Yeah, it's also another consideration for improvement. Hans? We haven't thought about it yet, but it would be a good idea. It would probably not be working too well for the dump truck. Maybe conveyor belt. Conveyor belt is probably more likely to use them. Potentially, it's just like I'm kind of afraid if we're using some kind of vibrate, it might like send like vibrations through the entire robot and potentially interfere with other systems. But yeah, that's a consideration. I actually have not. But yeah, we can definitely think about it.
I don't know the location. You might not know.
It might potentially be harder for like autonomy or something, but yeah, we can definitely think about that. Are those all the questions? Okay. Okay, I'm gonna hand it off to the position. I mean, drive.
Okay, let's get started with drivetrain. So we're going to start with a quick overview of our general plans. Our gearboxes are going to be linear. Basically that meaning we're not doing 90-degree gearboxes. Our motors are going to go directly into an onboard gearbox, and then we're going to have a 1-to-1 gear ratio inside of a gearbox to separate the motor and wheel shafts. We're going to keep our chain drive system. Bella's going to talk more about that later, but we're going to improve upon our chain tensioner system. If you were here last year, you know that that was a bit of a hiccup in drivetrain. So we're going to focus on actually doing the math beforehand so we don't run into those types of issues where our chain is like half too long or half too short. Our estimated system size is about 16 by 32 inches. That is outside to outside of the frame. And that gives about 6 3/4 inches per wheel, which practically means a 6-inch wheel with like a 1/4 inch of clearance and then 1/2 inch of play on each side of the robot, which is really right down where we want it to be. And then that's also 6 inches of vertical clearance from the ground to the bottom of a frame is what we're looking for. Our system mass goal, as outlined earlier by Peter, is going to be 20 kilograms this year. And our big focus is going to be looking at new wheel designs. We're going to talk a lot about that today. And then we're also going with box tube this year, not C-channel. We're going to do some sort of weight savings pattern. We haven't figured that out yet, but definitely weight savings. And we're going to consider different wall sizes this year too, if it makes our robot lighter. So there's a little bit more about the gearboxes. We got 200-watt motors this year, which is like, last year we had 30-watt. So it's like way better. So with the 51 attached gearbox, we need to be using about 18% motor power to get the same speed that we did last year. And that's with like significantly more torque. At the rated speed, we're getting like 60 RPM, which is about like 3.2 feet per second. So we can go really fast if we wanted to, or really slow with a lot of torque and precision. So I'm really happy with how that's going to look. As I mentioned earlier, we're doing that 1-to-1 gearbox inner gearbox ratio inside of our box tube. We're going to continue with that box tube design. A lot of the problems last year were with mounting the motors and encoders. Since these motors have built-in encoders, we don't have to worry about mounting encoders or designing for encoders. And with our 1-to-1 gear ratio, it should be a lot easier to put in access holes to easily attach the motor from the outside and not have to worry about getting an Allen key inside of a box tube.
All right, so do a quick run through. We spent most of our early time before SDR doing a lot of wheel design. So between that, I spent a bit of time just doing a quick trade study of comparing maintaining our chain drive system we had last year or maybe switching to a belt. From this little trade study, we found that overall chain would perform better, mainly due to like the durability and maintenance, but belt it had a couple points where it would overplay. We found in the power distribution that they would be about the same roughly with just eyeballing. There could be a problem with like belt slippage and stuff as it slowly extended. The belt system would overall be cheaper. That was its main plus, but we would have to, it wouldn't be a problem. We'd have to design directly around the belts just because we'd buy the exact size rather than be able to quickly adjust chain sizes. Yeah, we spent most of our time looking into just general cost, durability of the durability kind of coupled in with how long it would last, and also kind of can we replace, how often would we need to replace it? The power is just general power transfer from the motor to the front wheels, and then ease of use is how easy is it for us to get in there and make those changes if we need to. And from this, we kind of overall found that the chain would be better.
Okay, so in terms of frame, this is an image from the 2022 to 2023 competition run. The frame that year was made out of a U shape of C channels, and then during competition, it was observed that the frame experienced some bending issues up towards this front wheel. You can kind of see it. So that kind of led to our decision to go to box tubes for last year, and then also going with box tubes this year. So some just general pros and cons of box tubes and C channels. Box tubes have just greater rigidity and reduced torsion effects. Cons, it's generally heavier, and then we have a more limited access to the interior of the tube for like wiring and fasteners and all that. For C-channel, pros are it's generally very lighter, and then we have easy access to its interior. But then for cons, because it has reduced rigidity, it experienced torsion to a greater effect, and then it's minimal dust protection. Another con that's not on there is that they're not that fun to manufacture. A lot of the flexing that happens is just leads to a lot of difficulties. So with some just very rough CAD models and mass estimates, for a series of 4 box tubes, you can kind of see in that lower right picture, for a solid box tube based frame, it would be a mass of 3.65 kilograms. For a solid C channel, it's 2.8 kilograms. And then with box tube with weight saving holes, which is kind of just a rough cut of what this lower left image is, the mass goes down to 3.27. And then C channel with standoffs, which you can kind of see in the lower right, is 2.81. So another reason why we're just going to go with box tubes is the mass increase from doing box tube with weight saving compared to C channel standoffs. It's about a 0.5 kilogram increase, which is so negligible that there's no point with how many difficulties that we would get with C channels.
Okay. And then just to quickly recap some of the stuff we did last year and why we're not considering treads for this year. We did a trade study pretty in depth looking at wheels versus treads last year. And just to summarize, wheels are way more familiar, way cheaper, way easier to work with. We don't want to overcomplicate the system. It's also a lot less expensive and a lot less heavy. So that's why we're going with wheels this year. This year we came up with 3 unique wheel designs. One is more reliable, familiar, and then 2 of them are pretty experimental. We have a lot of drivetrain members this year, and we also have a lot of money this year. So I hope that for groups 1 and 3, even though their designs may seem pretty out there, you'll still consider them moving forward as viable options to prototype. Group 2.
Hey, so we're group 2, and just to really quickly go over our trade study. So we consider 4 types of wheels. The first being the domed outer rim wheel. That's essentially where the actual surface of the wheel that's touching the regolith during the competition is sort of domed, kind of like a very, very shallow hill. The second type is a bike spoked wheel. So like a bike, the actual structure of the wheel has spokes, like a bike spoke, and we can control the width and how thick and the material that these spokes are made out of. The third is a light alloy cast wheel. Essentially, like we use like sand casting or some other type of casting to cast the entire wheel at one go. Next is a solid external structure with a hollow inside. Essentially, this would be like a 3D printed wheel with the inside being mainly hollow. And the last is what we currently used in competition last year, which is a lawnmower wheel. And from our trade study, we found that the bike spoked wheel would be the most reliable, have the least risk associated with it. It is similar to the lawnmower wheel in many aspects, but it did also perform the highest on the criticality chart.
So upon like receiving feedback and more kind of thought, we decided that the bike spokes were just mainly just for weight saving, and a rim that's just a solid rim would be more sturdy, more efficient, and just kind of safer, kind of, because with bike spokes, say like the outer rim, which has to be rigid, like kind of deforms if it hits a rock. Trying to put a new spoke in would be very difficult on the field. So if we just had a solid rim, it would be easier just to kind of just to keep it strong and make sure it's and easier to repair.
So after that, we looked into a little bit more into grousers. So there's 5 grousers that we looked into that other teams use. And they were diagonal grousers, 2 offset rose grousers, wavy grousers, jagged grousers, and box grousers. And we decided to use a combination of the wavy and box grousers, which we have an image on the next slide for, because we thought it would be the most efficient, because most of the teams that used both or one of the wavy or box grousers actually did pretty well in the competition.
Yeah, can you actually go 2 slides? Yeah. So I'm going to talk about the design and manufacturing of the design that we kind of came up with. So this is the rough sketch of the design we came up with. You can see the box grousers, which is essentially the outer rim being extended out, and the curvy grousers, which should help with traction and structural rigidity. So the basic design is these 2 CNC milled aluminum sheet metal rims on the outside that are bolted together or some other form of fixation together. And then you have these grousers, which we think could be aluminum sheet metal. We could also CNC and then bend with little tabs on the end to connect into the rims. And then you also have the floor of the wheel, which could also be sheet metal bent into a circular shape around the inside. And then could you go back to the other one? So manufacturability, that's a big pro of this design. Almost everything would be out of sheet metal, and it would be very modular. And so it'd be very easy to iterate this design throughout the design process. And so we think that's a very good thing about this design.
For Team 1, we wanted to focus more on traction and sinkage because that was one of the main issues of last year's designs. Because every time they turned, they would often create little moats. So because of that, we focused more on more intricate wheel designs. This led to us researching 5 different wheel designs: mesh wheel designs, grouser wheels like last year's, snake wheels, hemispheric and steel wool wrapped ones. And from the wheel designs, we believe that the mesh wheel would be the best, although maybe harder to manufacture.
Yeah, so based off a lot of the feedback we heard from our trade study about the mesh wheel, the big problem that came up was easy manufacturability. We actually had a conversation with Sophia about that. And so we decided that we needed to adapt this design. So we transitioned away from having a mesh that essentially need to be a spring that's like stretched and then attached over 2 frames that are being bolted together. And we moved towards something called a coiled sheet metal design, which is basically going to be sheet metal that has a kind of cutout to it and is going to be stretched and then bolted onto frames. And I'll hand it over to my last teammate to discuss the specifics of that.
Yep. Yeah, so these springs would be maybe divided into 4 to 8 individual sections so that if one of them snaps, it would be easier to replace. And they would be attached to 2 central rims to hold it in place and help it go back to its original shape as it bends. And those rings would be attached to a central skeleton, which through the use of some metal rods, and that would help it stay in place throughout the whole time. That's it.
Hello. Hello, I'm the Team 3 representative, and we looked at our trade studies here. So first of all, we had the various grouser wheels, which were the staple wheel design, alternating patterns, and trapezoidal wheels. Just to briefly go over those, it was basically just heavy grousers versus spiked grousers versus a wheel that was shaped like a train wheel with grousers. We didn't go with any of those. Instead, we went with the dimple wheeled, combined with the curved on edges wheeled. So the dimple wheel was basically a subtractive wheel that had holes and dimples into the wheel. So the idea is that it would grip onto the regolith by simply digging itself into it. We made the selection based off of a few factors, but part of it was we mostly looked at the traction and sinkage, and we believed that the dimpled and curved wheels were best for that. So next up, we are taking a look at the pros and cons. And for the pros, the dimple wheels has a very wide surface area, so it would have a lot of ability to just like roll over the terrain and just it would have a lot of traction through surface area. Some of the feedback we got for that was that there would be a lot of slipping and sliding, so we decided to increase the size of the dimples and turn them into holes to prevent regoliths from getting stuck inside of them. And also, if it did, it could get pushed through to the inside of the wheel and come out the sides. Additionally, we also believe that this would have very good manufacturability. For instance, if we wanted to test, we could use ABS and just produce a lot of them for relatively low cost. For our final wheel design, we would probably use either PC or TPU to try and either get a flexible or stronger design for the final wheel. Some cons would be this is a very untested design. We do not know exactly how much traction we would have. And additionally, some of the other 3D printed materials, like if we wanted to go with carbon fiber or PC, that would be very expensive compared to some of our more traditional designs like what we currently have.
Okay, so that wraps it up for drivetrain. I'd first like to open the floor to questions. Let me speak this in the mic. All right, that's it for drivetrain. I'd first like to open the floor to questions about everything not the wheels, because I imagine there's going to be a lot of questions about the wheels. So everything before that. Absolutely, yeah. Okay, Alex. Okay, so the question is for the box tubes, are there going to be weight-saving holes on all components of our box tubes or just one side? Andrew, you want to talk about that?
So it's going to be something that's going to be very much looked into in the future as we proceed into actual design phase. And then the first thing we're going to have to do is decide what shape we're going to go with for the weight saving holes, right? That design, it's a very rough CAD that I did in 5 minutes, right? After we get design and all that, we'll do FEA to figure out what will be best. It's also going to be very determined by where all of our fastener holes are, right? Because obviously, there's no way we're going to have one entire side be able to be weight saving like holes like that. It's going to have to be spread out. So it's going to be something that I look into throughout the coming weeks.
The mass comparison on the right, is that for one box tube or for two?
The question was the mass comparisons on the right, are those for one box tube or two box tubes? Those mass comparisons are actually for our frame series where it's two box tubes on side and then supported by two inner box tubes. So it's for 4 total box tubes.
I would imagine that our plans, to answer your question, Alex, are to do weight-saving holes on all sides, though Andrew does bring up a good point, man, where our fasteners are, where anything else is attached, and where maybe P&H wants to run wires or other electrical components. Yes.
You mentioned that the motors are going to be like 80% power. If you look at like the efficiency curve and determine like where on that curve to like most efficiency,
I mean, I've seen the curve. Oh, sorry. The question was regarding that 18% power rating I have on here. Is that the most efficient? And the answer is, I'm not necessarily the guy to talk to you about that. It's probably more Alex. But I have looked at the curve, and from what I remember, it's interestingly flat up to a certain point, and so it doesn't really matter. Supposedly, this is a weird relationship, and I'm not electrical, so I don't really understand how that could be. But that's what the data sheet says. Peter.
So you said you're going to be going with linear gearboxes, right?
Yes.
But you've also said you're going to shrink the frame. Would you consider 90-degree gearboxes if we purchase them as opposed to manufacturing?
So the question is, I had originally said that we are planning on going with linear gearboxes and not going with 90 gearboxes. Will I consider going to 90 gearboxes? And the answer is, it is very unlikely. I think that we can get away with just offsetting our motors to be side by side, or then later adjusting the frame. I don't think it's ever worth it to go to a 90 degree gearbox. I think you lose a lot of your power, and I don't see the need for that right now. Yeah, Mike. I'm sorry, I didn't hear you. So the question is, have we done any calculations or FEA on the box tube versus C channel question, right? It's pretty early on, I think, for us to have fully done all those calculations. I know Peter had looked into some FEA, and it's something we're going to do moving forward. But no, we have not done any formal FEA analysis yet. Yeah. So the question was that I made these motors seem like they're just infinitely better than last year's, considering we only need 18% power to reach last year's. Are there any downsides to that? Yes, they are slightly heavier, and they are, as opposed to free from last year, they do cost money, but we do have a lot of money. So I actually don't see any real downsides. I think these motors are just a huge step forward going from brush to brushless. So no, I don't think there are any major downsides with these new motors. Yes, and all the sub teams are switching to these new motors. So this is not just a drivetrain thing, but yeah. Mike. Yeah, so the question was the reason that we, like in the past, we've been trying to switch to brushless motors and there's been difficulties with P&H and with dust protection. These are concerns that I can only really address the dust protection concerns. I'm not P&H. So I can't explain why they haven't been able to do it in the past, but yes, there are concerns with dust protection this year. There are exposed elements, and currently our plan is to design some pretty serious dust protection covers that just slot on over the motors and completely protect them. But we're going to have to do some considerable design research into making that possible. Yes. So what Peter just said for those on the live stream is that it has been confirmed that P&H is going to be able to make this work because the motors have built-in motor controllers. Any other questions about frame, gearboxes, any of our other plans besides wheels? Yes. It depends on where and how big those systems are. I could see with SCUP being in the middle that it might get in the way of our drivetrain motors, especially if we're offsetting them since it takes up essentially double the space horizontally. So that could be a problem, and we're gonna have to communicate extensively with excavation if they choose to go with SCUP in the middle of our robot to make sure that doesn't happen. Yes. Okay. So I realize I didn't mention the question for those on the live stream earlier, but Grant asked, with excavation considering a design that might go in between the drive rails, the frame rails, is drivetrain prepared to have to move anything around for that situation? And then Julian, as excavation lead, mentioned that they would likely move it forward so it doesn't have to interfere with any drivetrain components such as the motors. There's a question from. So 6-inch, the wheels are not 6.5 inches or six. So the question is for those here in person, if the wheels are 6.75 diameter, how do you get 6-inch clearance? Let me go back to that slide. Maybe there was a miscommunication there. It's 6.75 inch horizontally from the frame per wheel. So that would mean if you have a 6-inch width wheel, that you would also then have 3/4 of an inch for a mix of clearance between your actual wheel and your frame, and then also a mix of room to play around with on each side. 6-inch clearance is the distance between like the ground and the bottom of the frame rail. I hope that clarifies. Alex. Wheel diameter. So the question is, what wheel diameter are we thinking? Not fully sure yet. Last year we were like 12 3/8. So we're in the ballpark. The ballpark I'm aiming for is like 14 inches. So around that size, maybe a little bigger. Okay. Any more questions about that stuff before we move to wheels? Okay. Now we'll open the floor to questions about wheels. I imagine there's going to be a lot. Okay, Mike. Yeah. So the question is, why are wavy grousers better than straight grousers?
So we really researched that in our group, me and another member of the group, and we found that there's more surface area at any given moment in contact with the regolith on the grousers. So from our research and seeing what other actual companies have done, because companies like NASA and even Russia back in the day, they put wavy grousers on their rovers. So, and what we found out that they said is that it allows for more traction to be generated. And we're using that in combination with box grousers, so there's also less sinkage, and it allows us to turn better as well. Does that answer your guys' question? So what you said, just to paraphrase for people online, is that you're saying that the only surface area matters that is sort of perpendicular to the plane of the regolith? Okay. Right. Where we also read that it allows for better durability, but we didn't go too much into the math of how exactly the physics of it that allows for more traction. That's simply what we've read from multiple secondary sources. Right, we did read research studies, of course. We did not just take it from the first page of Google, like pseudoscience sites. But we didn't really look into the actual mechanism behind what they researched. Okay, we did not look into the exact numbers. Okay, yeah, but thank you for your question.
Peter.
How would it be easy to replace if the entire, if all the rims are single continuous sheet?
Yeah, just to repeat the question, if the design is to bend this one metal sheet all the way around, how is it easy to replace since that's something we mentioned?
Yeah, so making a singular sheet all around the wheel was the original idea, but I think I said that we would subdivide it into like 4 to 8 different sheets So that would make it easier to replace, as you wouldn't have to replace the whole thing every time. Does that answer your question?
Okay, great. I guess a follow-up question is, if you're subdividing into like 4 individual sections, what's the benefit of that versus just having a bunch of individual tabs, right? Like, why are you subdividing it into like 4 sections of like 4 sections of tabs that you vent versus just having each individual tab? Each individual tab you just vent and attach to the grid, right?
So the question was, if we're planning on subdividing it, why not just subdivide it infinitely so that each little section is its own individual tab?
Yeah, I guess that's a better idea, because our like subdivision idea probably came from the fact that in the start we wanted to make it a whole singular sheet. So we probably thought that dividing it would be better, but we probably will take into consideration what you're saying. Might be better.
Sophia? So the question was, since it may be possible that our robot does hit rocks, is it possible that the big gaps between each of these little pieces of sheet metal, is it possible that it gets stuck somehow on a rock or breaks?
Yeah, so this was something that we talked about during the iteration process, which is just that the spacing between those cutouts can be variable. And this was actually part of our reason for maybe wanting to have it be made in sections. This is just maybe a slight counterpoint to the idea of making it individual tabs, which is that if you have single, or I guess section sheets, you can pre-machine those small spaces in there and then stretch it over, as opposed to having a million individual tabs that you're trying to do precise small spacing with to provide a small enough clearance that you're not going to end up snagging on a big edge like that, as you mentioned. Okay. Yeah, the statement that was made by Alex was just that autonomy is maybe not necessarily going to be able to prevent us from running over big rocks, and that was a major motivation for this design, was having an exterior part of the wheel that is going to be essentially deformable in some sense, but then hopefully returning to its original shape, just so that we can avoid getting stuck on things. You had your hand up first. Yeah, so the concern that was voiced was that we would have kind of like a traction issue, as you were saying, which is that if you have thin sheet metal pieces that you're trying to have the exterior of your wheel made out of, you might not be able to push off as well. This is something that we were a little bit worried about, and I think that is going to require some consideration of like the thickness of the sheet metal that we're using to make the pieces, and then also how much the weight of the robot pressing down is going to help you develop traction, and yeah, as well as the size of the gaps. And we were possibly thinking of putting some kind of texturing on those sheet metal pieces that are going to be wrapping around. So as An said, this is probably our most experimental design, so it's going to require a lot of thought and development. Yeah, so the question that was voiced was about whether or not we could run into a breakage issue if you have a thin piece that's wrapped around. Yeah, this is definitely something we considered. We were thinking, is it going to be good to go with aluminum, or are we going to try and go with steel? We were going to have to evaluate a trade-off between like a thin steel or a thicker piece of aluminum. We definitely have to do a lot of research into that, but yeah. Oh man. Peter again.
What mechanism will
Yeah, that's again a material question. I think if you want to handle this, okay.
So the idea behind the bending of the aluminum or steel, whatever we decide on, is kind of mimic more of a spring like it, where if you bend the metal, it has a higher tension. So when it like flattens out when it hits the ground, it'll bend back. Uh, so the materials. The question was, what materials were we thinking of making the sheets out of? And we were thinking either between some sort of strong, some steel for the strength of it, or aluminum for its more lightweight capacity. And we haven't fully looked into the trade-offs of both yet, but those are our two considerations currently.
So just maybe a clarification. We are not doing the mesh exactly anymore. The idea was we go to this sort of springy flat metal sheet. So it's not a mesh anymore. Right. So we switched off the mesh because there were concerns of how you actually manufacture that. We talked with Sophia, who had some experience trying to make those in the past, and it's practically impossible for what we can do here in Lunabotics. So this is like the best approximation that we think.
Yeah, going off of that, the middle sketch is more like what the final wheel design will look like, where there's the outer spring-like sheets, and then there's an inner spoke to hold it all together. Peter.
So currently for the 3D print, actually, so the question was about manufacturing the third wheel design and about the 3D printing feasibility of that. So
For the size of the wheel, roughly the 14 inches, for 3D printing feasibility, it would be mainly determined by what filament we're able to use. When looking into types of filaments, different types of filaments require different types of 3D printers. And so, depending on what we can find on campus, that would determine if it's printed in either parts and then put together some way that has not yet been determined, or if it could be printed as a whole thing. The goal is to print it as a whole thing, but if we can't find a 3D printer large enough, then it would have to be printed in parts and then assembled.
another thing I'd like to add on is also that with our current wheel design, as you can see, although this is a very rough model, it is very much a patterned model. So we could print it in multiple patterns and just like cut the wheel design in half and then just screw them together, something like that.
We have not thought about that, but that's a really good idea. Oh yeah, sorry. The question was, have you thought about using a metal hub and then 3D printing the TPU and attaching it to the hub? Yeah, here.
So the question was about the regolith going through the holes and out the sides, and about how that might sound like just digging it in. So one thing I'd like to say about that is, first of all, when we say coming out the sides, it wouldn't just be going out the sides. It'd also be going back out the holes. And what I mean is, as the wheel's rotating, it's going to move and jumble the regolith around just by virtue of it rotating. So that's going to move the regolith around. And if it happens to come out the side, it comes out the side. If it happens to come out the hole, it comes out the hole. So that would not require it to dig itself in.
Yeah. Definitely for this design, I can pass it off to other groups after. Oh, the question was width of the wheels. So for us, we definitely are looking at making it much wider because then you get more surface area and then it won't sink in as much.
The planned target is 6 inches per wheel. Yeah, 6 inches of clearance, 6 inches of wheel. So it's convenient, or maybe inconvenient or confusing that those are the same dimension. Alex. That's a really good question. The question is if excavation went with a bulldozer, the concern is there's a lot of traction that would be required to make that mechanism work. Do we have a wheel design that will be able to support that? It's a complicated question because we won't really know until we're able to test. And we are kind of looking to move forward with all 3 of these designs in prototyping, but design 2 is probably the most likely to work because I think with those grousers that can be customly designed, you can probably get the most traction out of those. So that would be my answer, just based on what I know about the design so far and where we're at. But it's difficult to say right now, and it's especially difficult if we don't even know if excavation is going with that design. Yes. So just so I'm making sure I hear this right, the question is, do any of the wheels provide an advantage with rotation and turning and maneuverability? I think traction was one of the biggest factors that all the groups considered. So ideally, each of these groups is going to be able to get good traction and great control. That's also a big reason why we're making the wheels a lot wider. Is hopefully that every single one of these wheel options will be able to have great maneuverability through the terrain. Yes. Yeah, so the question is, have we considered making the frame even narrower? Right now, we're looking at probably 12 inches inside if we use 2x2 box tube. And then the motor, like the combination of the motors and the gearboxes are expected to protrude a little under 7.5 inches. So in theory, we could have like a 7.5 inch wide inside diameter or inside distance there. I don't see the reason to go to that extreme, especially since like 6-inch wheels are already pretty massive. I don't think we need to go any more than that. But Andrew, do you want to comment more?
So the other biggest factor with, or my concern with making the frame any thinner is I've heard from software that the more square the orientation the wheels are in, the easier it is able to drive and turn in general, right? So that's my concern with making any thinner. The other thing is also making it thinner also reduces the room for our X-step system, right? So there's a few concerns that would go into making it narrower.
Peter. That's a great question. The question is, have we thought about how we're going to test these wheels? I think each group might have a slightly different answer, but prototyping, hopefully using Alvi. Since we're kind of considering using the exact same shaft size as last year, these wheels should be able to pop right on for any of our prototypes. Potentially just one and seeing how it can interact with the other ones. Potentially scale down for all the designs, scale down so we can experiment with scaling and things like that. Attach it to what? So Sophia's crazy idea is to attach our wheel prototypes to a power drill and then just try running that. Um, I think it is a crazy idea, but I think it's also a good idea. So we'll see. Yeah, Mike. Okay, so Mike's idea is to test by manufacturing only, for example, like the bottom 10%. That's easy with the printing designs, or like some portion of the entire wheel, and then adding a weight to it, and then testing how much force is required to move it and break that static friction. That should give a good idea as to how much traction you're getting out of each side wheel. I actually think that's a great idea. I think it's something we should consider moving forward with our prototypes. We do have a lot of members, so I think that's definitely something we can do. Yes. So the question is, have we done any calculations on how thin these spokes would need to be to support the wheel or mass? Again, it is early on to have those types of calculations ready. That's more of a PDR, if not a CDR type of question, I think. Yes. So the question was, it wasn't really a question, it was more a concern. How we're going to bend this sheet metal around into such a large diameter, especially being so wide and thick. But Alex mentioned that Bechtel might have some resources that we'll be able to utilize to manufacture that. I also don't think, I think the wheel design you're talking about with like last year or the previous wheel design was 1/8 inch. We might not need to go that full 1/8 inch, depending on how many grousers. So that's something we consider, but also with the tools at Bechtel. Sorry? We are doubling the width. So yeah, it will be hard. And we were going to seek advice from you as to how you actually did that. If you want to answer to that right now, like how did you do that? Yeah. Okay. I'm not going to explain that for the live stream. Well, you want me to? Okay. Yeah. Okay. So the idea that was brought up is pretty complex. Let's talk later about that because that sounds interesting. And I'm not quite sure how that would work into this design. Yeah, Mike. Sorry? Say that? Solid what? A solid hub? Are you talking about between the two rims? Or like this hub itself? I see. So to make it like just basically cover this entire thing. Okay. So the idea was to cover essentially the entire opening of the wheel with a thin piece of aluminum or other material to stop regoliths from getting inside the wheel. I'm not too concerned with regoliths building up in here, but I think it's also a good idea to consider, especially since 16th inch aluminum plating shouldn't add too much weight. It's just something else that has to get done. But I think that's definitely something we'll take into consideration. Alex. That's a great question, and it's actually something that kind of completely fell off my radar until now. So the question is, last year, so there were situations where it was desirable to run the wheels in locations where it would probably not be greatest for the floor. Are there plans to make these wheels acceptable and capable of driving on like a regular floor and not in a sand pit? And right now, we haven't really thought about anything, but I would guess that Group 1's and Group 3's designs might just by nature be possible. Like, or we use a separate set of wheels or old wheels. What was it? So Andrew had also mentioned the idea of making wheels that are like the same size, but just adjust that these aren't instead of grousers, but some sort of soft material like a tire. That's possible. It's just something else that we have to budget and make, which takes time. It's not the biggest concern right now, especially with the new pit that we're getting. So. Yeah, that's also a really good idea. We still have some leftover lawnmower wheels from Mike's original wheel design from a couple years ago. Alex mentioned that we could potentially just slightly modify the hubs on those to accept the drivetrain wheel axle, and then just use those. That's definitely possible. It's actually probably the most likely. So that's a good idea. Okay. Great.
Okay, that was a good first half of SDR. We have more presentations after lunch. So if any of you guys want to take home some bagels, please do. I can't eat 30 bagels. Okay, we're all going to Fiesta, so you can join if you want. Thank you. Yeah, I don't know what to do with that, you know? Should I say something on the live stream? Okay. We're stopping for lunch, but we will be back with a new live stream link. So in about 1-ish, we'll start up again.